Yulun, and the next talk is a mini talk. It contains only 5 slides, but they are critically essential. So if the speaker will try to present them quick, you may try to stop or ask questions. So it is most essential part in the practical skills for the group for the whole year. And we are not doing this meeting, series of meetings for developing or proving equations, but the idea is that the orthogonality of electronic states is maintained if geometry is steady, but if the nuclei are subject to change of interatomic positions, either elongation, contraction, as Diane, Nathan, and all other members of Professor Krzyzewski group doing, will be subject to break of orthogonality relation. And if the positions of atoms are shifted due to molecular dynamics, it also will be a reason for orthogonality between quantum orbitals is not maintained. And the practical steps needed to quantify this effect will be presented by Yulun.
So suppose you have already completed the MD calculations. So you want to get the energy fluctuation, you need this script. So this script needs 2 arguments. So this is just an orbital interval. This is the starting orbital. This is the final orbital. And you just follow these steps and you'll get this kind of a figure. So this figure shows the evolution of quantum orbital energy as a function of time. Because since my duration of trajectory is 1,000 seconds, so here we can see 1,000 seconds. This is energy.
How would this image look if the temperature is 0?
There is no fluctuation.
So the increase of temperature would be resulted in larger amplitude of these fluctuations.
Right.
How should we interpret if there is something like this? Looks like quasi-periodic, but if suddenly one orbital energy goes from one band to another one, or there is something dramatically changing, how to interpret it?
There's some band crossing.
Or some reactions. So if the system is far from equilibrium.
Mm-hmm. So we may want to extract intermediates from molecular dynamic trajectory, and we can use this kind of code. So there is one point we should pay attention, because this code is based on VASP4. So if you are using VASP5, then you need to modify the postcard. So this is the postcard file from VASP5. So we need to delete this additional line. After we do that, we can successfully load this code. So if successful, then some files like P000, P990 pop up. And this file corresponding to geometry of intermediates. Questions?
I definitely have a question, but I do not know how to formulate it. DM may have questions.
What question might I have?
What are these P000 files?
What are these P000 files?
It's just snapshots along MD trajectory.
And what is the format of these files?
It's basically like the postcard.
So
their coordinates.
Yes, and they are in the VASP format. There will be, after running this command, there will be 1,000 postcard files, each of which corresponds to one subsequent step along the molecular dynamics trajectory.
And for each of those postcards, you have to calculate energy.
Later on, yes. Yes.
At this stage, this file just corresponds to atomic position.
So you calculate them all at the same time?
No,
They
no.
don't
One
depend-
runs molecular dynamics, which is a standard task for us, and then with the script, one extracts the trajectory which is hidden in the out car and exit car into so many individual files.
And they're all saved. Yeah.
They are saved in the directory where you run this script.
The out car, or reach the out car.
Originally, they're saved in the out car, but this it's kind of unzipping from one file into 1,000 files or whatever how long your dynamics is.
Okay, then another script takes two at a time and performs single point energy calculation.
Yes, and it will be covered in the next slide. But this is could be interesting for a group of Professor Kureski because it is a replacement of what you do in your normal modes when you shift positions
Mhm.
of each ion to the left, to the right, one by one.
Yeah.
And in some
Yes.
sense, you also have set of different geometries for which you compute the electronic structures and then use it for couplings. Here, these shifts are not by moving individual atom in a organized way, but it is a simultaneous motion of all atoms along the trajectory. But it serves the same role as in your approach shifts of individual atoms. Make sense?
Yes.
So next step is to calculate nonadiabatic couplings. So these are necessary files for the coupling calculations. Basically, we need 10 files. So the income. So here is the format of input order. This is the starting orbital, final orbital. So typically, I just choose maybe 160 orbitals. It's 80 orbitals below HOMO, 80 orbitals above LUMA. And key points protocol, this is just a standard MB calculations. So we need a special income coupling. It is stored in this location. And also we need this 1,000 files from MD trajectory. We also need some script files. So we need a Corey script. This is a standard for running any calculations in us. Also, we need a bit script file. Here is what it looks like. And we also need some exe file. So for this one, we just extract some orbital energy, like energy bar. This one calculate oscillator strength. This is an overlap between snapshots at adjacent trajectories. And this is the location of the exe file, and this is the location for the sh file. So after you have prepared all files, you can just submit your job with this command.
So it is what Diane was asking about. The script inspects the P001 files with coordinates one by one. So there is a 1, 2, 3, 4, 5, 6, 7th line in the script that runs over this time steps, and in each of them it runs last, and then it does extract the orbitals and compares orbitals at the previous step and the current step. Okay. So what is the output? What does one get in the directory upon completion of this job?
Some coupling files will pop up.
So what is the what are the names and what is the contents of these files?
Yes, it's coupling dot some number.
So it's same format as for this positions, like for P000, it will be corresponding coupling 000. So as many coordinates, as many couplings.
Differ by one.
One less.
Yeah,
Okay, and what is inside these couplings files?
it's just a transition probability.
But how is it numerically organized?
It's in a matrix format.
So it's a square matrix, and what are the indices of the square matrix?
It depends on your output. Depends on the input overlap. For here, it's 162, so it's 162 by 162.
So indices for this matrix are indices of orbitals involved.
Mm-hmm.
So it transitions from one to another orbital.
Mm-hmm.
So it generates 1,000 square matrices.
Right.
Okay. Thank you. And it's time for questions.
Okay.
Please.
562 is all orbitals?
No. It's
Just-
just 80 orbitals about Yulun.
So 562 minus 401. And that's like your orbital, the number.
401 is LUMO? 401 is HOMO?
401 is
No.
401 would be like
401
normal minus 70.
401 is the number of occupied?
no, 401 is HOMO minus 80. So HOMO is
Lowest orbital.
181.
Is the meaning of this input overlap in Yulun's talk
Okay.
is the same as meaning of input overlap in David's talk. So window of orbitals involved in the calculation.
Okay, so HOMO is somewhere between 401 and 562.
Exactly. Yes.
What is one? But you don't know.
It's a heritage.
It's vestigial.
But you don't know which one is HOMO, and it doesn't matter.
You do know when you prepare this input.
But not from input overlap.
Hmm?
But not from input overlap. You don't know which one.
You don't record it. The input overlap doesn't need this information. Because later on, partial information about which is occupied, which is unoccupied is stored in the occupation. Especially if the
okay.
system was good. More questions to you?
Dan, how long is your talk?
Depends.
So,
When you were practicing it in the bathroom?
I was.
Okay.
This is my practice.
How many slides?
33.
Okay. More
So-
questions to
how does this approach scale with the number of atoms? What's the latest on the same question we have?
let me translate your question. Will this method be substantially slower if you double number of atoms?
Well, I like my version fine. Or triple, quadruple.
It's probably because previously I was doing some calculation for 200 atoms, and the coupling calculation maybe several weeks. And
Several
yes,
weeks. It's
Yeah.
like from this fence and until March. Okay, what I'm
So-
my question is I'm trying to compare the two approaches. The first is when I compute the normal modes and so on and so forth. So I know it takes 6n, where n is number of atoms of energy calculations by EFT software. And then I know response of my system to small displacements of atomic coordinates. So how many steps do you need here as a function of number of atoms to compute your thermal averages?
I understand what she's talking about. I'll translate.
Okay.
So if one is doing normal modes calculations or molecular dynamics, the time used to compute single point will increase with size of the system in both situations. But for normal modes, the number of single point calculations will be increasing with size of the system. Like if you go from 100 atoms to 200 atoms, it will be like proportional increase of number of steps, 6 and whatever.
600 to 1200.
Is there, in this approach, is there a necessity to increase number of single steps? Is there a necessity to increase the length of trajectory if one takes larger system?
What's the meaning of trajectory here?
Should one use like 2,000 steps instead of 1,000? Would it give any benefit for bigger system or?
I guess for the following calculations for non-radiative rays, there will be some difference. But if you are looking for some qualitative trends like initial, they are basically the same.
So no matter how big your system is, the length of trajectory can be kept in certain limits.
It's problematic, isn't it? I mean, if you want to simulate chaotic thermal motion of your system, you need to move, ideally, each atom multiple times, right?
We can continue the argumentation, but the practical convergence is achieved very quickly.
What's that practical convergence?
The results, depending on the length of trajectory, starts converging if trajectory is longer than 320 seconds to less than L1.
So see, no matter how big system is.
Yes. Okay, but thank you once again. I'm inclined to present today.
Wait, design is not there.